Hey everyone, we're about to wrap up here on our look at volumes of rotation or just volume of solids here on calculus. There is one more section after this that we're going to call optional, in that it's not part of the AP Calculus curriculum, but it is part of the calculus curriculum. So if you're interested in that, go ahead and click that. Otherwise, this will be our last day in volumes. So let's go ahead and take a look at what we got. We got washers and donuts. And what you might suspect is that this is actually going to be something called the washer method. And you're right, this is the washer method. That's why we got them there. Sometimes people call these donuts or the donut method, probably because donuts are a lot tastier than washers. And well, if that's the way you feel about it, then that's the way you feel about it, right? So the washer method is called a washer method because in all of our volumes, there's going to be a hole on it. Same thing with donuts, of course. So to get us started, we're taking a look at this relatively simple geometry problem. We were supposed to find the area of the region formed when a circle of 2 centimeter diameter is cut from a circle with a 5 centimeter diameter. So, go ahead and figure this out if you like. The volumes, they just need to be subtracted. So we're going to do volume 2. No, why am I doing 2? Volume 1 is going to be the big volume. And that's going to be equal to pi r squared. We'll call this capital R squared. And the big volume, the big circle has a diameter of 5. So the radius is going to be 5 halves. So that's good enough for me. But I guess a lot of people want to see that as 25 over 4 multiplied by pi. Now the smaller circle here, that's going to have volume 2, which is pi little r squared, which we can say is pi times 1 squared, or just pi. So the volume of the shaded region is just going to be equal to volume 1 minus volume 2, which is 25 over 4 pi minus pi. And if you want to consolidate that, that's 21 pi over 4. Not too difficult of a geometry problem for most of you. But this geometry problem is exactly what we're going to be doing with the washer method. We're going to find the volume of a large circle, and we're going to subtract from that the area of a large circle, and from that we're going to subtract the area of a smaller circle. Let's take a look at what we have here. Okay, so find the volume of the solid of the region in the first quadrant bound by these lines, 1 over x plus 1 and x equals 1. And we're going to rotate that around the line y equals 1. So here is the line x equals 1. X equals 1 is here. Let's do that in a different color. X equals 1 is over here. We're in the first quadrant, so we're bound by here and here. And then we're also bound by, of course, 1 over x plus 1. Now the thing to notice is when you rotate this shaded region about our axis of rotation, we're going to create a hollow solid. There's going to be like a hole in the middle of it. And we can tell that because if we draw a line from our axis through the region to the other side, we notice that there is a section here that's not shaded. Or another way of putting it is the axis of rotation is not a boundary curve. And I just noticed that I actually wrote that over here. The axis of rotation is not a boundary curve of the region. And that's going to tell me that we are going to create a solid that has a hollow section in the middle of it. So some people, find this really difficult to visualize. These are just some steps from a computer output that kind of helps you see how this gets formed. It's a very interesting solid. Notice it's a cylinder, and it's got this, section of it cut out of the middle. I think maybe the best way to see it is this one right over here. We've got that hollow section right over here, which is this hollow section over here. So we already have our corners, 0, 1, 0, 1, 0, 0, 1, 0, and 1, 0.5. So that's going to give me my x minimum is 0, my x maximum is 1. So now we have to talk about the radius. This time, we've got to talk about 2 radii, because we have a smaller radius, which basically spans the hollow section, and then we have a larger radius, which goes to the edge of the solid. Now, over here, this is probably the best way to see it. This right here is our small radius. It's the radius of the hollow section. Okay, so this is going to be a difference of y coordinates. The y coordinate up here is 1. The y coordinate down here is that curve. So when we get back over to this, the smaller radius is the axis of rotation minus the function, which is 1 minus 1 over x plus 1. Now the larger radius, let's do this over here, and I'm going to do this a little bit over on the side. The larger radius is this whole thing right here. That's the larger radius. And the larger radius is always going to be 1. Because the distance from the axis of rotation to the x-axis is always going to be 1. So for these washer methods, you're going to have to contend with 2 radii. And that's really one of the bigger challenges here. So here's our larger radius. Here's our smaller radius. And let's get going with this. Next is going to be our area formula. And this time we are going to have 2 area formulas. So the first area formula is the larger one. The larger one I'm always going to denote with the capital letter R, and the smaller one's always going to be the lowercase letter r. So the larger is going to be pi r squared, and the big radius is 1. So we'll put a 1 there. And then the smaller circle cross-section is this radius, 1 minus 1 over x plus 1. So here are the 2 area formulas. And when we integrate this, all we need to do is find the areas separately and subtract them, or find the volumes separately and then subtract them. So this is, again, from 0 to 1, 0 to 1. And then if you take a look at these, you can actually combine these 2 integrands. Although that's completely optional. You don't have to do this. So optional, we could make this the integral from 0 to 1 pi, and this is going to be the big radius squared minus the little radius squared dx. Now that's totally optional. There's no real reason to do that other than it looks nicer on the calculator. But you have to know that this is two integrals being subtracted from each other. That's the base here. So I'm going to go ahead and put these together. So we got 0 to 1, put the pi on the outside. And this is 1 squared minus 1 minus 1 over x plus 1 squared dx. Okay. Grab our calculator and get this calculated. And integral from 0 to 1. Ooh, you know what? I need to put a pi in front of this whole thing. So let's get that pi in there. Pi integral, and this is going to be 1 squared. And that square is not really necessary, is it? Minus something else squared, and what is going to be squared is, oops, 1 minus 1 over x plus 1, the whole thing squared, dx, and that should give us a result pretty quickly, 2.784. So we've got the volume is 2.78437 cubic units. Okay, let's try this one. Find the volume of the solid when the region in the first quadrant bound by the lines y equals 1, y equals x squared, is rotated about the x-axis. Okay, so right now I notice that the x-axis is not a boundary curve. So that instantly makes me think, is this a washer method? Let's graph to see this. Probably don't need to use a calculator to graph this one, but I'm going to go ahead and do that just for the visuals. We've got 1 minus x and x squared in our y equals menu. We'll start with zoom standard. We'll see how this goes. There's that diagonal line. There's y equals x squared. Ooh, okay. So we need the region that's bound by those two curves only. And that looks like this kind of a crescent shape here. I'm going to zoom box into it. So zoom box. Let's get to where that lower corner would be safely. And let's go to the opposite diagonal corner. Maybe right around there. And let's try and get this to be the same proportion as the viewing window. Okay. All right, so notice that the region that we have here is not bound by the x-axis at all. So that means we're going to create a washer. With our graph here, we need to locate the coordinates of these corners right here. Those are the only corners on our graph. So let's go over to our calculator and we'll go ahead and second calculate intersection. Let's see, curve 1 at curve 2, and let's take a guess. That looks like it's close to negative 1.7. So let's say negative 1.7 as our guess, and 1.618. Quickly label that onto your work. X equals A equals 1.61803. So I can use the letter A in my calculations now. On my calculator, I want to go and store that value. So let's get that value up there. And there it is, negative 1.618. Take that and store that as A. You've seen me do this a few times now. Go back to the graph, and let's find the second intersection. So second, calculate, intersect, and let's see, curve 1, curve 2, and that point of intersection looks like around 0.5. So let's take a guess of 0.5 and see how close we are. Oh, 0.618. Okay. Same thing. Let's go to the home screen, call up that value. Notice that x has changed to that value now. We're going to grab that and store that as b. Back on our paper, we're going to write down that the x-coordinate equals b, and which is equal to 0.61803. So now I can use b in my work. Now, radii. Let's identify our axis of rotation, and let's do that with the squiggly red line over here. Here's our axis of rotation. We've got to figure out our two radii. So the first radii, r1, that's going to be the distance from the axis of rotation to the curve that's furthest away from the axis of rotation. So that's this right here. That's a lot of red on this paper, but hopefully that won't get confusing. So that's our big radius, the distance from the axis of rotation to the big curve. Now the equation of the big curve is y equals 1 minus x. So this radius is equal to 1 minus x minus, now the x coordinate down here is 0, so minus 0. So that's our big radius. Our little radius is going to be the distance. Let me clear things up a little bit. Our little radius is going to be the distance from the axis of rotation to the closest curve to it. So this is going to be the little radius. Okay. The y coordinate here is x squared. So it's going to be the y coordinate on top, which is x squared, minus the y coordinate on bottom, which is the axis of rotation, which is 0. So this is, I don't have a number, but this, we'll call this f of x minus axis of rotation. And over here, this is g of x minus the axis of rotation. Okay, we've got that. So our area formula is going to be pi r squared minus pi r squared. Okay, which is pi multiplied by 1 minus x squared minus pi multiplied by x squared squared. And last, we're going to go ahead and go with the integration. That's a ridiculously small box for an integration, don't you think? Let's go ahead and put it together. This is going to be the integral from a to b, which are crazy values, so I'll just write a and b. And then our area formula is pi 1 minus x squared minus pi x squared squared dx. So at this point, I'm saying, you know, we needed a calculator, or you had to have a calculator to get those points of intersection anyways. So as long as you're using your calculator, you might as well integrate with your calculator. So let's grab our calculator and we'll integrate. Whew. Math, integrate from A to B, because we stored those values already. Now, I don't remember which curve is which, so I'm going to go take a peek. It looks like y1 is going to come first. So this is going to be pi times y1 squared. Pi times y1 squared minus pi times y2 squared. Dx. All right, that should get it done for me. 11.708. So we've got a volume is 11.70802 cubic units. So this washer method is literally doing two disk methods and subtracting them. That's all it is. Here's our important ideas. Computes volumes for, or the washer method is going to compute volumes for solids that have a hollow. So same idea for the radii, only now we have big radius and small radius. And then we can either put the two integrals separately like this, or you could put them together, or we can do kind of what I did here, which is a strange combination halfway between here and here. So the integral from a to b of pi big R squared minus pi little r squared dx, which is probably what I would normally do anyways. Okay, so let's take a look at this check your understanding. A part of the droid MG923 is made by injecting metal into a die with a shape modeled by revolving the area in the first quadrant bound by the coordinate axis y equals cosine x about the line y equals 1. What is the volume of the part? Okay. Let's take a look at a graph of this, and I'm going to go ahead and graph this kind of old school wise. Let's take a coordinate axis, and we only need the first quadrant. Now the first quadrant needs to be a boundary curve, and we need a cosine function. So this is kind of what the cosine function looks like. And remember what this question says. It says the boundary curve is a coordinate axis. So if this is a boundary curve, and this is a boundary curve, and this is a boundary curve, then the region that we're looking at is right over here. Now we're going to rotate this around the line y equals 1, and we definitely have a place where y equals 1 is, right over here. So let's draw that line. There we go. So that's our axis of rotation. We're going to be circling that. And I notice that that axis of rotation is not a boundary curve. So this is going to be a washer method. Okay, we're going to start by getting all the corners of the region. This corner is x equals 0. This corner over here, well, I'm getting a little bit lazy here. Let's get the coordinate here. That is 0, 1. This coordinate here is 0, 0. And this corner right over here, that is pi over 2, 0. So it looks as though That's going to be A, and that's going to be B. So A equals 0, and B equals pi over 2. Step 2, we should look at our radii. So our big radius is going to be from the axis of rotation to the furthest point from it, which is right over here. The y-coordinate here is equal to 1. The y-coordinate here is always equal to 0. So the big radius is going to be equal to 1 minus 0. Now the little radius is going to be the distance spanning from the axis of rotation to the inside curve, which is basically the radius of the hollow section. So here, the y-coordinate equals 1, and here, the y-coordinate equals cosine x. So the radius is equal to 1 minus cosine x. Okay, step 3. What is my area formula? The area formula is equal to pi big R squared minus pi little r squared. And I think this time we're going to gather those pi's together and say it's pi big radius squared minus little radius squared. Or pi 1 minus 1 minus cosine x squared dx. Now I'm thinking ahead, and that 1 minus cosine x, that's going to be a bother when I try to integrate. So I'm going to expand that right now. That's pi 1 minus the quantity of 1 minus 2 cosine x plus cosine squared x. Again, I'm trying to get all of this simplification done before I get to the integral. So pi, 1 minus 1 cancels. This is going to be 2 cosine x, and then minus cosine squared x. Well, we can use that power reducing formula for, well, no, let's not get ahead of ourselves. Cosine squared x. Now we're going to use the power reducing formula to simplify that. So that's pi 2 cosine x minus 1/2 1 plus cosine x, sorry, cosine 2x, and we might as well simplify that out one more time. So pi 2 cosine x minus 1/2 minus 1/2 cosine 2x. So that's going to be my area formula, which takes me to step 4, which is the integration. So the integration, we say the volume is equal to the integral of the area formula from a to b. And my a was 0 and my b was pi over 2. My area formula is pi, and that's 2 cosine x minus 1/2 cosine 2x minus 1/2 dx. All right, now the integral stuff is going to be easier. So this is pi. The antiderivative of cosine is negative sine. The antiderivative of cosine 2x is negative 1/2 sine 2x. And the antiderivative of 1/2 is negative 1/2 x. And we're going to cap this from 0 to pi over 2. And I think I got those integrals slightly wrong. The integral of cosine is positive sine. Oh boy, bother. Let's erase that and change our signs back. There we go. So that's better. All right, I think we're ready to substitute things in here. So this is going to be pi. 2 times sine of pi over 2. Sine of pi over 2 is 1. Minus 1/4 of sine of pi is 0. Minus 1/2 multiplied by pi over 2. So that's my first substitution. Minus the second substitution, which is 2. Sine of 0 is 0. Minus 1/4 sine of 2 times 0 is sine of 0, which is again 0. Minus 1/2 of 0. So this time, the second substitution gives me a 0, but that's not always the case. And we just need to simplify this first one, which is, what is that? 2 pi minus pi squared over 4. So the volume of MG923 part is 2 pi minus pi squared over 4 cubic units. So that seemed like it was a pretty long one, but again, calm down. This is just the disc washer done 2 times for every washer method that we do. So keep that in mind. Keep in mind that you're going to use the washer method if the axis of rotation is not a boundary curve. Keep calm, and I will see you next time we get this, which is going to be the optional lesson. Right, the optional lesson. Have a good one.